Okay, welcome to chapter 20. We're going to look at some more applications of differential calculus in this chapter. In chapter 19, we saw curve sketching, so being able to graph good sketches of a whole bunch of different functions just by using calculus. That's awesome. The two big ones in this chapter, I think, come later on in sections C and D with optimization and related rates. Here in section A, we're going to do kinematics part 1. Part 2 comes later on once we've studied integral calculus. So we got to wait a few more chapters to really see the end of this topic, but we'll look at the basics of it right now. So kinematics are just, that's just motion, physics stuff. So we're going to be talking about position, velocity, acceleration, all that good stuff. So we begin with displacement. I just said position a moment ago. Position and displacement are very closely related. They're almost the exact same thing. So we've got some object, we're calling it P for point. It's a point that's moving along a straight line. So we'll say it's moving along the x-axis, say. And it's not necessarily moving in the same direction all the time. Maybe it starts off moving to the right, then it changes direction and moves to the left, and then it goes back to the right again. Whatever, you could imagine this dot kind of moving right and left, yeah? So its displacement is a function of time. Maybe s of 1 is equal to 3. If that's the case, that means that after 1 second, the point P is over there. Perhaps s of 4 is equal to -7. That would indicate that point P was out here. In this case, the 1 and the 4, they're not any part of the coordinates. It's strictly moving right and left along the x-axis. The output tells us where it goes. So x is actually a function of t. I'm saying x because I'm thinking about an x-axis on a graph. Actually, in this case, it would be the s-axis, the position or the displacement with respect to time. Why do we use an s for this? That actually comes from a Latin word, which I have no idea how to pronounce. Anyway, if the displacement was positive, it would be located, the object would be located to the right of the origin. If the displacement was negative, it's located to the left of the origin. If the displacement happens to be equal to 0, then it's sitting back at the origin. So far, so good, right? So what's the difference between position and displacement? Well, so that's the big difference between the two. We need to read any problem we're faced with. And of course, it doesn't need to be a horizontal line, right? We could think of like a vertical line, in which case, if the displacement is positive, we'll interpret that as the object being above its starting point, negative below it, whatever. But we're always dealing with this, this simple motion as just being along some straight line. Now, we know that velocity is a rate of change of position with respect to time. So, if we wanted to find the average velocity of an object moving in a straight line, we'd use our slope formula, because that's going to get us the average rate of change in between two particular points in time. So again, time is the input here, but do you see in that formula y1 minus y2, or I guess it says y2 minus y1 over x2 minus x1? It's the same idea here, because the position is the output, time is the input. So that would get us the average velocity. How do we get the instantaneous velocity? Well, that means we're taking a derivative function. So the velocity at a particular time is equal to the derivative of the displacement at a particular time. And we can calculate that with our limit definition or whatever. We're not going to do that, right? We're just interested in this right here. Likewise, the average acceleration is going to be the secant line slope in between 2 points where the output is the velocity and the input is time. Acceleration at a particular time is equal to the instantaneous velocity at that particular time. If you're really interested in studying physics, then you can keep going past this. The rate of change of acceleration with respect to time is jerk. The rate of change of jerk with respect to time is snap. And then from there it goes to crackle, and from there it goes to pop. And no, I'm not making those up. I don't have a clue what they like mean. You know, in my own personal experience as a human being, I can understand feeling a change in velocity, but I can't really imagine what it means to have a change in acceleration, or certainly not what it means to have a change in crackle. I don't know. That said, we're talking HL math here. I'm not thinking about the real world. I'm thinking about the beauty of ideal mathematics. So of course we can take higher derivatives. Why shouldn't we be able to? Let's just give them fancy names. Anyhow, let's just do something there with the average rates of change. First two, pretty straightforward. Look right here. We're just using our average rate of change formula for velocity. Means we're going to take the position at time 5 minus the position at time 2 divided by 5 minus 2. Simplify. We got -4, and the units, since it's velocity, are going to be meters per second. For part B, average velocity, same idea. This is just a little weird. Instead of going from 2 to 5 seconds, we're going to go from 2 to 2 plus h seconds. Whatever, we're just going to put in 2 plus h instead of 5 there. Simplify, simplify. We got -1 minus h. Again, meters per second. IB tends to write meters per second, by the way, using exponential notation. You see it in both of these. M times s to the -1. I don't care how you write your answers. They're going to do it that way. This third one, I want to calculate a limit. Haven't done that in a while. Well, first of all, recognize that this is really the exact same thing as what we had here, right? If those 2's cancel, then we've got the exact same expression. We're just taking the limit as h approaches 0. We've already done the algebra to figure out that we're here. So if h approaches 0, then this is really just becoming -1 meters per second. And what does that mean? Comment on its significance. Well, it's nothing super important in life, but it is the instantaneous velocity of the particle, specifically at 2 seconds. Of course, if I was really interested in finding out what that was, I would just calculate v of t. That's the derivative of s of t. That's going to be 3 minus 2t. Put in t equals 2, and of course 3 minus 4 is equal to -1. All right, the remaining problems we look at will deal with instantaneous velocity and acceleration. So kind of recapping what we said earlier, v of t is equal to s prime of t, a of t is equal to v prime of t, which is equal to s double prime of t. These two right here give us the initial conditions, because that's when time is equal to 0. We're going to be considering the signs of these various functions. So let's think about what they mean for our moving object. If the displacement is equal to 0, then the object is at the origin, or I would prefer to say the object is at its starting place, wherever that might be. If the displacement's positive, it's located to the right. If the displacement's negative, it's located to the left. If velocity is 0, that means it's not moving. It is at rest. If velocity is positive, it is moving to the right. Velocity negative, moving to the left. Acceleration positive means that the velocity is increasing. Acceleration negative means the velocity is decreasing. Remember that the velocity could be negative but increasing, or it could be positive but decreasing. Last thing, speed is not the same thing as velocity. Speed is the absolute value of velocity. If we find out that the sign of the velocity and the acceleration are the same, whether they're both positive or both negative, then the speed is increasing. It could mean that the velocity is positive and getting more positive. It could mean that the velocity is negative and getting more negative. In both of those cases, the object is moving away from its origin at a faster and faster rate. So its speed is increasing. Anytime that the velocity and the acceleration are opposite, the speed is decreasing. That doesn't mean that the velocity is decreasing. It means that the speed is decreasing. As soon as you got your head wrapped around all that, we're ready to dive in and look at a kinematic problem. Look at this. There's so many questions that we can answer with regards to kinematics. And some of these, I think, are better answered using integral calculus. As I said, we're doing part 1 for kinematics today. But we can still work our way through them using only what we know now. So let's go. All right. Part A, find expressions for the particle's velocity and acceleration and draw sign diagrams for each. That's easy enough. All right, we have got a function is s of t up here, so we're just going to differentiate, right? So there's v of t, 3t squared minus 3. We factor it out completely. We got this easy sign diagram. We've got 1 and negative 1 are the two values of t we're interested in. We're only interested in this problem for t greater than or equal to 0, so we can toss out the possibility that t is equal to negative 1. Otherwise, if that restriction hadn't been given, then we'd want to still include it, even though that's kind of like a weird time machine thing. It doesn't make sense in these problems to have negative time. But anyway, moving on. That's velocity. That means we need to differentiate again to get acceleration, which is just going to be 6t. Awesome. So that's only going to be equal to 0 when t is 0. So that makes its acceleration is positive all the time. Marvelous. Part B, find the initial conditions. Okay, so what's s of 0, v of 0, and a of 0? Easy to calculate. Oh, doesn't quite fit on the screen though. There we are. So we've got, starts at 1 centimeter. So this one's not starting at the origin. Its velocity is negative 3, so it's not starting at the origin. It's starting 1 centimeter to the right of the origin, and it's initially moving to the left. Its velocity is negative. Okay, part C. Describe the motion of the particle at t equals 2. That just means, like, in a sentence, say what the conditions are when t equals 2. Kind of like what I just said out loud for t equals 0. So S of 2 is 3, so it's located 3 centimeters to the right of the origin. It's moving to the right, since it's got a velocity of 9. And then, since we have an acceleration of 12, that's a positive number. Its velocity is also positive. That means that the object is speeding up as it's moving to the right. So that's what it means by describing the motion. Find the position of the particle when the change in direction happens. Change in direction means that the velocity changes from negative to positive or from positive to negative. So we're going to take our velocity function, not currently on screen, but we saw it just a moment ago, and we're going to set that equal to 0. That's only going to happen when t is equal to 1. Just to remind you what it was right here, and t equals 1 was the only value for it. So that's the only time when there's a sign change. And the question was, what's its position? So that means we have to calculate what is s of 1. And we've got negative 1 is the answer there. Draw a motion diagram. I don't think the IB has ever asked for something like this before, but this is an example of what a motion diagram might be. So it's just a way to like visualize how this thing is moving over time. So we said it starts 1 unit to the right of the origin, and it starts moving to the left. We know that when it gets to the position -1, it turns around, and then it's moving to the right forever and ever after. So that's a motion diagram. Part F, when is the particle's speed increasing? Well, remember that its acceleration was always positive. So its speed's going to increase whenever the acceleration matches the velocity. So really, as soon as it turns around, then its speed's going to be increasing forever. So that was at time when t equals 1. So for t greater than or equal to 1, our speed's going to be increasing. And final question, what is the total distance traveled in the first 2 seconds? So this is the part that would be, I think, better answered with integral calculus. We'll answer a ton of questions like this later on once we can do integrals. But as I said, we can still do this now. And the answer to this lies in the motion diagram, because we can see that in the first second of motion, right, we started here, and that was 1 second later, we established earlier. So how far has the object traveled so far? 2 units, from 1 to -1. And then t equals 2 is over here. How far has the particle traveled in the second second? Another 4 units. So we've got 2 units and 4 more units. That's grand total of HL Math, boys and girls, 6 units. What were the units here again? Centimeters? Centimeters, yes. All right, so that's the end for kinematics for now. I wouldn't worry too much about these motion diagrams. Like I said, the IB's never, to my knowledge, asked for one. And as far as finding out what the distance traveled between various times are, like I said, once we know integrals, there's a much better way to do that. I almost forgot. I got to show you this one. I've seen at least 2 instances in which the evil IB has tried to trick children with problems like this. This kind of stuff really makes me mad. This is just, I don't know. This is an unnecessarily annoying problem. So, I don't know, take a look at it. What do you think? What do you think the acceleration should be? Here's a wrong answer. The wrong answer is to say, okay, this is a negative s to the -2. So we take the derivative of that. That gives me an acceleration of 2 s to the -3. Put in 50 into that, because 50 centimeters, and that's s, so that's position. Great. So that's 2 over 50 cubed. Maybe you're clever enough to realize, okay, this was in meters and this was in centimeters, so we shouldn't be putting in 50, we should be putting in 0.5. Okay, so then that's going to give us 2 over, well, 0.5 is 1/2 cubed, that's going to be 2 over 1/8, that's going to be equal to 16. Okay, 16 is the right answer. No, it's not, because acceleration with respect to time is equal to the derivative of velocity with respect to time, which is equal to the derivative of position with respect to time. T needs to always be our input values in these. In this example over here, our velocity was written with respect to time. Our acceleration was written with respect to time. In this example, our velocity is written with respect to position. Oh, that means when we differentiate here, we got to use the chain rule. So we've got velocity is equal to -1 over s squared. We're going to take the derivative with respect to time because we want to find out about acceleration. So we'll do that to both of these. Left-hand side, derivative of velocity with respect to time, that's acceleration. right-hand side. We're going to take the derivative of negative 1 over s squared. Okay, that's going to start off the same. We got 2 times s to the negative 3. Chain rule. We need to multiply by the derivative of s. Think of this as like if it had been d dx of negative 1 over y squared. We'd have a y prime here at the end. This is just an s prime. But wait a second. What is s prime? That's the derivative of position with respect to time. What is the derivative of position with respect to time? It's velocity, and I know what the velocity is here. It's negative 1 over s squared. Putting this all together, our acceleration is negative 2 over s to the 5th. Putting in 0.5 in for s, that gives us a final answer of negative 64 meters per second squared. Please be on the lookout for crap like this. They've done it more than once, and they're mean, evil people for it, I think. Anyway, that's Kinematics Part 1.